Hello and welcome back to Global Math Mentor. This is another lesson on A-Level Pure Mathematics 3. Today we're diving into one of the most visual and elegant topics in complex numbers, loci. In this lesson, we'll explore how conditions on complex numbers can translate into geometrical shapes like circles, lines, and perpendicular bisectors on the Argand diagram. If you've ever wondered how algebra meets geometry in the complex plane, this is the topic for you. So grab on your notebooks, let's get started. So this is the required skill, which is given in the syllabus document. So students should be able to illustrate simple equations and inequalities involving complex numbers by means of loci in an Argand diagram. And they have given some examples. You can see there's an inequality, then an equation on the second place, and then another thing given. So I know they look a bit weird, but let's break them down one by one. So I'm going to be listing all the possible loci and I'll explain them one by one. You don't need to explain them on the exam. In the exam, you're just required to apply those ideas, right? But I feel like understanding them in a detailed way is important. So in my next videos, I'll solve the exam questions and there I will just straight away apply these ideas. Okay, let's get started. So first thing you must be familiar with is something like this. If this is written somewhere, real of z equals to, let's say, k. So what kind of a locus is this? If you remember from the Argand diagram, the real part is the x coordinate of the point, and imaginary part is the y coordinate of the point. This is the Argand diagram. So, for example, if I take a point like this, you remember from your Cartesian system, if this is, let's say, 1. So, how do you used to write this equation in your normal Cartesian system? You used to give its equation like x equals to 1, which is a vertical line. So, x equals to 1 is a vertical line in the Cartesian plane, but instead, if you look at the Argand diagram, this same locus can be written as real of z equals to 1, or whatever the point is given. It might be real of w or real of u or real of v. So in this case, I'm just taking this. So make sure you have noted this down somewhere. This is type 1. So I can write the name as well. This is vertical line. All right. Okay, similarly, now you know I don't need to explain it that much. Im z equals to, let's say, if it's c. So imaginary part of z is always like a horizontal line. So if I make a line here, remember from your Cartesian system, if this is, let's say, 2, you say this line's equation is y equals to 2, but in a complex plane in Argand diagram, you will write its equation like im z equals to 2. So let's highlight this as well. And I'm going to be giving the name of this type of locus. Oh, by the way, locus means path, trajectory. So it's like a path this complex number traces on an Argand diagram. So this is the horizontal line. All right. So let's talk about some of the other types of loci. You will come across this kind of locus quite often in an exam. So make sure you remember this form. So what does z minus z naught, the modulus sign, equals to r means? So this z naught is a fixed point, and this z is a variable point, which is obviously tracing out this locus variable point. So by the definition of the modulus of the difference, it means it's the distance between a fixed point and some variable point, which is always equal to r. Does that ring a bell? It's going to be a circle in an Argand plane. So let's highlight this, and I'm going to give you an example just to make you understand why this is a circle. Remember, you do not need to explain this in the exam. The only requirement is to apply them in the questions. Okay, so let's take an example, and I'm going to be taking z to be x plus iota y, which is like a general variable complex number. And on an Argand diagram, this point will look like xy, where x is the real part, y is the imaginary part. Let's take z naught to be some number 2 plus 3 iota. And this is going to be 2, 3 on an Argand plane. And let's say their distance r is equal to 4. So what happens if I write this form? I'm going to be doing it here. Xy and minus the 2, 3. We know that this represents distance between the point xy and 2, 3. So this is equal to 4. I'm going to be applying the distance formula on the coordinates. So this is going to be x minus 2 whole squared plus y minus 3 whole squared. A square root equals to 4. So if you square both sides, this equation is going to look like this. Well, what do you know, guys? This is the Cartesian equation of a circle. And you know from pure mathematics, this is 2, 3 is the center and r is the radius, which is 4 in this case. I hope you understand this one. The type 4 in loci looks like this. Z minus Z1 modulus. It means distance between Z1, which is a fixed point in this case, and Z, which is a variable point, like discussed earlier, will be equal to Z minus Z2. Now, you can see that if you think about it, a variable point in an Argand plane is equidistant from two fixed points. So, what does that mean? Think about it. Have you come up with an answer? It's going to be the perpendicular bisector between Z1 and Z2. And it will look like this. Okay, so that's how the perpendicular bisector looks like. So remember, no explanations required. You'll be able to recognize the locus and sketch it and sometimes shade it as well. An interpretation can be done in these ways, like they might ask, like, what does this locus represent? So you'll be able to answer them that this represents. So let me just write the name as well. Perpendicular bisector. And here's an example which I can use to. Okay, let's do a shading example. So for example, if someone asks you, z minus I is greater than z mod. So, how do you understand this thing? Number one, forget about the inequality. Just think about the equation. So, I'm going to be writing it in the coordinate form like z minus what is just I in an Argand diagram. Remember, if you haven't worked on the basics of complex number, I'm going to be sharing the link in the description where there is so much about the basics of complex number and all the mechanics you need to understand. So this is just 0, 1 and on an Argand diagram. So 0, 1. And if no point is there, what is the point? Origin will be the point from which the distance is measured. So what does this mean? That the distance of z from 0, 1, listen to me carefully, is more than distance of z from 0, 0. So stop and think about it. Will z be closer to 0, 0 or will z be closer to 0, 1? You get it? It will be closer to 0, 0 since its distance is less from 0, 0. So let me just sketch it over here. Okay, let me just make some space and I'll show you the sketch of this inequality over here. So let's make an Argand diagram. Remember, it's just a sketch, real and imaginary. So this is a 0, 0, and this is, let's say, a 0, 1. First, the equidistant mean that it's going to be a perpendicular bisector between these 2 points. So this is equal distance, and that is a 90. So now, since it's an inequality, it's not just a specific set of points, it's a range of solutions. So this is the region which you will be required to shade in the exam. In my later examples, I'll make things more challenging and complex by adding in different types of locus in a single question. That is what you need to master to cover the exam questions. Another type you will see quite often in the exam is argument of z minus z naught equals to theta. And this one has a unique name. We call it the half line. So why do you call it a half line? I'll explain it in a while. This has to do something with the angle, remember. It's argument of z minus z naught. So it means this is how it looks like. If z naught is a fixed point and z is a variable point, it's an angular relationship between them. So you make like a horizontal, and this angle is the argument between z and z naught. So that, why do you call it a half line? So just an extra tip. In polar system, there is no y-axis or x-axis. You can search polar axis if you want to get a detailed view of that. So in polar system, you just have a pole. So this line is not a complete line. The complete line goes on both sides of pole. Since we sketch only one part of it, that's why it is known as the half line. I hope you understand. So again, the explanation is just for your concept. You are just required to sketch it in the cases given on the exam. Recognize and sketch. Let's take an example where you can understand. Well, I can give you more than one example. So if it's written somewhere, argument of z minus 2 equals to, let's say, pi over 4. All right. So you can see that the fixed point is just 2. What kind of a complex number is 2? It's 2 plus 0 iota, which is a 2 0 on an Argand diagram. So I'm going to sketch it and see how does it go. Imaginary part, real part. This is 2 0. Okay, so what is pi over 4? Remember from your trigonometry course, pi over 4 is an anti-clockwise angle because it's a positive value. So I'm going to be sketching it this way, and this is how it looks like, pi over 4. And well, that's your locus. That's it. Okay, so let's take another example. I'm going to be sketching it here just to show you like there can be other ways in which this is tested. So if I have argument of z minus, let's say, iota and equals to 3 pi over 4, right? This is another example. So make sure what's the fixed point? You sketch the Argand diagram, place the fixed point where it is I. So we know already it's a 0, 1 on an Argand diagram. Okay. What's a 3 pi over 4? It's 135. So it's an obtuse angle. So how do you sketch it? It's going to be here somewhere, a 45 on this side. So I'm going to be putting a 3 pi over 4, and that is your locus. You can see that the fixed point is 0, 1, and the locus is 3 pi over 4 angle from the horizontal. This is the half line. Let's take some example now where you'll be given a combination of loci and you'll be asked to shade and do all sorts of things. Now I'm going to solve an actual exam problem. On the sketch of an Argand diagram, show that the point representing the complex number, this. Okay, so let's place the point representing the complex number. So if this is, let's say, 1 and 2. So we know that root 3 is more than 1. So it's going to be here somewhere, right? That's the point 1 and root 3. You can always check with your calculator like what exactly is, it's around 1.7 something. Okay, so they're saying on the same diagram, shade the region whose point represent the complex number z, which satisfy the inequalities this one and this one. So here's the key line. Forget about the inequalities right now. First, sketch your loci. Understand, recognize them, and try to sketch them. So the first one, z, I'm going to factorize the minus out. It will look like 1 plus iota root 3 and is equal to 1. So why did I factor out the minus? Remember that the form that I just shared earlier, you can rewind and check it again. The plus isn't the correct form. It has to be minus. Okay, so this is a circle and its center is 1 and root 3 and its radius is 1. Well, I can sketch this. So in the actual exam, you can take the compass, and you can sketch it in a correct way using the compass, because otherwise your circle will not look very decent and nice. Okay. So, and remember, this has to be, okay, let me just use technology, but you will be using the compass. It has to be tangent to the y-axis. Oh, it's still not a tangent, so I'm going to be putting it right here. Okay. Why a tangent? Remember that its radius is 1, so it has to touch the y-axis here somewhere, right? Okay, so what about the next locus? It's arg z, which is, I can write it z minus a 0, 0, which is the origin. If no reference point is given, 0, 0 is your reference point, and put it equal to pi over 3. Now remember from my argument lesson, again, if you haven't watched, you must go back and check that again. So argument is usually the tan of the angle. So z minus the origin, this distance is tan of pi over 3. And tan of pi over 3, you can check in your calculator or use the special triangle to check this out. That the reason why I'm telling you this is you'll find out in a minute. I just noticed that this point is special. This is a pi over 3, this is a 90, and this is a pi over 6. So that's the magic, the special triangle. So I know that this argument, this loci, will pass through the origin. And why is that so? Remember, guys, this is a root 3. You can check this vertical distance, and this is a 1. So this angle, if this is pi over 3, it will pass through the center. You might be asking a question, do I need to be this specific while sketching? I mean, if it's better if you understand things that way. So remember, argument has a connection with tan. It's the angle opposite of adjacent, because every complex number in the xy plane on the Argand diagram is represented like xy, and y is the vertical coordinate and x is the horizontal coordinate. So to get the angle, you use the tan ratio, right? So this is the case. So I've sketched my loci. Now comes the shading part. So if they say it's less than, okay, let me just show you. If it's less than equal to 1, it means, let me just write it here, inside the circle, because you are trying to shade 1 or less. So the radius is 1, so it will be inside the circle. And when they say that the angle is less than equal to pi over 3, it means it's below this half line. So this is the desired region which you need to shade. I mean, you can shade it anyway, but that's the correct shading, right? I hope you understand this one. Here's another actual exam question. On a sketch of an Argand diagram, shade the region whose point represent the complex numbers satisfying the inequalities, this one, the first one, and this one. If you want to give it a go, you can pause the video and try it on your own and then come back and check my work. Okay, let's solve it together. So the first part, you can see that it's z minus, factorize the minus out. So the 2 plus I can now be written as 2, 1. And this is equal to 1. Remember, while sketching, you do not need to write inequalities. It's just a sketch. Remember, it's just a sketch. So let's put this sketch over here. And this is going to be like a 1 and 2. And this is a 1 and a 2. This is imaginary part. Remember, it's an Argand diagram. So real part. Let's put another point 3. Okay, 2, 1 is the center of the circle. This is the center of the circle. So it should look something like this, right? Okay, let me make it a bit bigger. So remember, you need to take your compass in the exam. The reason I'm trying, because its radius is 1, and this is how it should look like. Okay, this circle. So 2, 1 is the center of the circle, and the radius is 1. Okay, next bit. It's z minus iota. What is iota on an Argand plane? It's just 0, 1. And the other point is, put it equal to z minus 2. 2 is the 2, 0 on the Argand diagram. Okay, because 2 can be treated as 2 plus 0 iota. It's a complex number. So 2, 0. So this is a perpendicular bisector. Let me just use another pen for this one. So this is a 0, 1, and this is a 2, 0. Just connect it and you can form a perpendicular bisector like this. You don't need a compass and protector, just use a scale. Remember, it's just a sketch. And another thing, you are not required to actually give the equation of the perpendicular bisector because that is a different concept. Like in geometry, you know how to do this. If you want to quickly check it, you can find the midpoint of 0, 1 and 2, 0, and then find the gradient and flip it upside down with a negative sign, negative reciprocal, and that way you can actually find the equation of this perpendicular bisector. And you can find the y-intercept as well. But again, that's not the requirement of the question. Okay, so now comes the shading part. They are saying it's less than equal to 1. So this means, this first part mean we need to shade within the circle, right? And this one, if this is less than equal to, it means this part, I think often students get confused by this. That's why I'm giving like a slow explanation. Listen to me very carefully. Z's distance from 0, 1 is smaller as compared to Z's distance from 2, 0. So if its distance from 0, 1 is smaller, it will be closer to 0, 1. That's the point. So you can shade the part which is closer to 0, 1. And that is your first part. Let's take a look at the second one. They are saying calculate the maximum value of argument of z for the points lying in the shaded region. So I need the maximum value of argument of z. So argument of z, how do you understand argument of z? Remember, if no other point is given, origin is the point. Argument means angle. So this is the angle from the origin. You need to connect the shaded region with a line from the origin. Now there are different angles which I can form in the shaded region, but what will be the max angle? Well, you can check if I make a tangent over here, that's going to be the maximum value of the angle, and that is your angle, this one. Let's call this theta. So I think I need to zoom this out to zoom it in, sorry, to explain you in detail for the next part. So I'll share it in the next clip, right? So this is the zoom part of the same diagram. If you do not know how did I get this thing, you need to rewind it and check again how did I get this diagram, right? Okay, so I wanted you to look close and focus what's going on. So I'm going to be connecting the center with this tangential point. Okay, and this center with the this point as well. There is a circle theorem. Let me remind you from your GCSE. So tangents from external point to the circle are equal, like this point and these tangents are equal. So we know that this another thing related to that same property is it's a kite since radius is equal to radius. So kite has one line of symmetry and a kite can be divided into two congruent right angle triangles, right? So I hope you understand this thing. So I'm going to be using this property to quickly check what is the angle since I'm looking for the angle theta, which is here. You can check this angle theta, right? So let's take this kite. It's something like this. I'm extracting that. You don't need to extract it. You can use your existing diagram to solve it. But since I'm explaining it in detail, I'm extracting it. So this is what the kite looks like. I mean, you should consider it's identical, these triangles. So this is one, this is one. I'm looking for this angle. So instead this, I can use the half part of it and get the angle. Okay. So can I get this length? Look at this triangle. The base is 2 and the height is 1. So, and it is a right angle triangle. So I can use Pythagoras theorem. This is 2 and this is 2. Since again, tangent from any external point to the circle are equal. This will be root 5. And well, I don't need this length anyway. I can use the same existing length to get this angle and then I can double it. Let's call this theta 1 and theta 2. And that will be the greatest value of the argument of z. Argument of z, as I told earlier, is the angle from the origin. Let's get this angle. So I'm going to be using functions tan inverse, and my calculator right now, Desmos, is in radians, so I don't need to worry about my answer. This is 1 bit. Let's double this answer, and this is going to be 0.9273. 0.9273. If I give this answer correct to three significant figure, it's going to be 0.9, 2, and 7. That's my answer. Well, that's it, students, for today. And in this lesson, I'm just going to give you a quick summary. I discussed each type of locus that you will face on your A-level mathematics exam. Another interesting thing, we merged different loci and used the ideas how we can use these combined loci and find the shaded regions. And in the end, I solved some exam questions where you can observe how not just the sketching part, shading part, you might be asked to find like the shortest or the greatest distance or the shortest angle, least angle or the greatest angle. So if this video helped you, make sure you comment, like, share, subscribe, and share it with your friends. This is Global Math Mentor, over and out.